Another kind of graph is called a histogram, and it's awfully similar to a bar graph. It looks the same as a bar graph, but there are a couple of significant differences. In a histogram, the bars involved in the graph always touch one another. That is, they're shoulder to shoulder, those bars are. And the bar width represents some kind of quantity. Let me show you an example of a histogram, and then we'll talk about how to structure or how to build the histogram in just a minute. This is a histogram having to do with 9th grade reading scores. And on this axis, I have number of students, some number of students, and notice it runs from 0 to 10. And along this axis, I have the reading test scores. Now, notice that the bars in the graph are shoulder to shoulder. They just are right up against one another. And notice that the width of the bars are just numbers. This is an interval of numbers, you see, represented by each of these boundaries between the bars. Now, the bars are not called bars. They're called classes. And here, then, we have, let's see, 1, 2, 3, 4, 5, 6, 7, 8 classes. And they are just classifications, or they are intervals of numbers into which these reading test scores have been placed. Now, we can read our histogram like this. The frequency involved in the histogram is read just up and down, just like a bar graph would be. You just kind of look at the top of the bar or the top of the class, and you read over to the left. So the frequency for this particular class would be, let's read over here, it's between 8 and 10, that would be 9. So there are 9 students whose scores fell within this interval. Now, let's talk specifically about some terminology. We already talked about the notion of class. Those are the various intervals into which the test scores fall. And it's important to know that those intervals are all equal in width. That is, this interval and this interval, they represent the same width or the same opportunity for the numbers of scores. Now, if you look closely here, this is 49.5, this is 69.5, that width then is 20. This width is 20, that width is 20, and so on. So it's the same all the way across. Now, lower and upper class limits refer to the smallest and the largest test score that can fall within a particular class. For example, if we're talking about, let's say this class, you see, then what's the lower limit and the upper limit? Now notice that the boundary is 109.5. And if we're talking about reading test scores, let's make the assumption that those scores are whole numbers. So the scores are whole numbers, and that means then that if the boundaries have a decimal associated with them, that the whole numbered test score will fall distinctly within a particular class. And that's a rather important aspect of histograms. We don't want a value in our graph. We don't want a value that is associated with this graph to fall right on a boundary. We would like for each class to contain distinct members involved in whatever we are evaluating here. So we accomplish that here. If the reading test scores are whole numbers and the boundaries are decimals, then our values for reading scores fall distinctly within here. Okay, good. Now, lower and upper limit. The lower limit, the smallest test score that can fall within this class, if the boundary is 109.5, the next highest whole number would be 110. So the lower limit here within that class would be 110. Now, what's the upper limit? Well, this goes up to 129.5. The largest whole number that is below 129.5 is 129. So 129 then is the upper limit. So lower limit, upper limit. The next item here that I have written is class boundaries. Now, those boundaries can be found. We'll see how to find them in just a little bit. But if we're looking at a graph like this, all we need to do is take the upper limit in one class and the lower limit in the next class and sort of average them. You see, it's the number that's right in between those two. So if we're thinking about the upper limit in this class as being 129, and let's see, the lower limit over here would be the smallest number, which is larger than 129.5, that'd be 130. So 130 is the lower limit here. So 129, 130, you see the decimal, which is right in between these two, is 129.5. That's a way of thinking about that boundary, that class boundary. Now, class width, we've already talked about a little bit. It is the sort of the range of numbers, the interval of numbers that fall within here, and we're talking about an interval of 20 values. We can find that by taking the difference in any two consecutive lower limits. We have 110 to 130, you see, and that's a difference of 20. So these widths are 20. Another way would be to take a difference in boundaries, successive boundaries, and that difference is also 20. Frequency we talked about earlier, and that just has to do with the top of the class and reading over to the left. So the frequency here would be 9. The frequency on this particular class would be 2. It's the number of test scores for this application. It's the number of test scores that fall within these various intervals. That's all there is to it. Now, midpoint, the midpoint of a class is sometimes called the class mark, and in some histograms you'll see that the class mark indicated on the histogram. That midpoint can be calculated in a couple of ways. You know, if it's called a midpoint, just think about intuitively how to calculate a midpoint. We can take the lower limit, upper limit, add them and divide by 2, and that'll give us a midpoint. We could also utilize the boundaries in order to figure midpoint as well if we wanted to do that. Well, how would we construct this? How would the information come to us originally, and how would we structure this histogram? Well, let's look at that, and we're sort of backtracking here. Let's presume we don't have the histogram right now. We begin with raw scores. So we would have a list of test scores. Now, I happen to have listed the test scores in an order here, and it isn't necessary to have them listed in order like this in order to begin the process. What you do need to do, though, is when there is an array of values or scores that we want to make a histogram for, is to identify the lowest score and the highest score. That's kind of important. It's also important to identify the number of classes that you want. Now, I suggest that you use a number larger than 5 and a number smaller than 15 for the number of classes. If you get to 15, then, well, it's a matter of interpretation. If you have too small a number of classes, then you're really not going to generate any significant information from the graph. If you have too many, same idea. You just it skews the evaluation of the information. 8 is a good number of classes to use in a histogram. Well, let's suppose we decide then that we're going to use 8 classes. So we decide on the number of classes, and now we want to decide on a class width. Well, to decide class width, you take the largest score, subtract the smallest score, and divide by the number of classes that is intended. And when we perform that calculation, we get 154 over 8, which is approximately 19, right about 19. Now, this class width should simply be convenient for you. A class width of 10 or 20 or 30 or 50 or 100. Those are convenient sizes for class widths if you can possibly achieve that kind of thing. Now here, we're very close to 20. So since we're just over 19, I've just bumped it up a little bit, and we'll make 20 the class width. Now, you know that because this class width of 20 is slightly larger than the actual calculation of the difference between the smaller and larger divided by the intended number of classes, that this would be an exact width that would contain all of the values from smallest to largest. Now, we're bumping that up a little bit to make it convenient. So we're going to have sort of a little bit of slack on one side or the other, or we could balance the slack on both sides. Do you know what I'm saying about that? About the slack? We have a little too much room on the outer ends of this. And we would have even more room if we were talking about with, let's say I said, let's bump this up to 25, or let's bump this up to 30. Gee, if we bumped it up to 30, you see, and tried to move our intervals all the way out to 30, we're getting a little far out there with 30, and we're going to be beyond the interval of numbers that we have. So there is some danger in doing that. We want to bump it up just a little bit, not too much. So we have to be a little bit careful. And the bump up can be on either side. Like here, our smallest value is 51. So we might begin the interval at, say, 50. That's what I'm doing here, is I'm beginning it at 50. Now, if this number, this smallest number, were 53, I might still say the beginning of this is 50. Now, by saying that it's 50, we're creating a little slack, a little interval in which there aren't any scores, you see, on that end. And we might end up doing the same thing on the top end as well. Let me break in here and tell you, this might help you with your homework. The text follows the convention of always using the smallest data value as the lower class limit of the first class, and that's going to help you to generate histograms that match the answers in the text. Well, okay, so we decide on class width, and we know from the lowest score that we have to have the beginning of our graph starting at a value below 51. So I'm electing to start at 50. And now we're going to establish the limits. Now this means the class limits involved in the histogram. So we're going 50, and we said the class width is 20, and class width is calculated as the difference in successive lower limits. So the next lower limit after 50 would be 70, and the next lower limit would be 90, the next lower limit 110, and 20 is 130, and 20 is 150, and so on, all the way until we have 8 classifications. All right, now, what about the upper limit? Well, let's see, we're going 50 to 70. What's the score below 70 that falls into this? Well, it would be 69. And now we can just go down the line over here for the upper limits and add 20. You see 69 and 20, 89. And then you see 90. And then 20 with 89 is 109. And 20 and 20 and 20 and so on. Okay, so we established the limits. Now what about the boundaries? Well, the class boundaries can be calculated. As we calculated earlier, we can say, well, if we take the lower limit of one class, the upper limit of another class in succeeding classes, I should say it like this, the upper limit in one, the lower limit in another, then we take the average of those two, add them and divide by 2, and we have the boundary. Another way to think about it is like this. Let's just back off 5/10 right here from 150 and make this 49.5. And now between 69 and 70 is 69.5. And now we're thinking about that class width as being 20. And so the upper boundary for this class is the lower boundary for that class. And you see, and notice the difference in 20 here. And so we could go add 20, add 20, add 20, add 20 all the way down. And these rascals over here are just automatic from these. You see the upper boundary over here is the lower boundary for this particular class and so on. So it's pretty easy to structure this in a sort of a chart form. All right, now once we have our structure for the histogram, we know how many classes we're going to have. We could actually make the axes involved. How tall do we make the bars, or how high do we make those classes? How do they go? Well, we have to count some kind of frequency involved in the list of numbers. Now, I had the numbers written in some kind of order, so it's pretty easy to do that. An aid to doing that would be to make a tally for the frequency of test scores that fall within a certain bound or within these limits. You see, the number of scores that fall between 50 and 69 inclusive would be 2. And I just made a mark every time I saw a number that's within this this range. And in this range there were 3 values, and in this range there were 2 values, and in this range there were 9 values. And to make the tally marks for 9, I went 1, 2, 3, 4 slash, that's 5, and then 1, 2, 3, 4. Now, and then after the tally marks are made, you just count them up, and you have a frequency. And that allows you to understand then how tall to make those bars. So when we make the graph, we would come back over here, we would begin to structure the graph almost like a bar graph. That is, we have an axis here, we label this what we want on this axis, label what we want on that axis, label what we have as the title of the histogram, and we're going to make our bars or our classes just right up against one another, because after all, this boundary is an upper bound for that class and a lower bound for that class. So these have to be shoulder to shoulder. And then we just start with what we had over there as our the lower bound for this class and its upper bound, and using the same width, you see, just march right across and put those bounds in here. And then with our frequency information, we know how tall to make all of the classes. And we're done with our histogram. In the previous example, we were talking about the frequency being used for our classes. That is, the number of students whose scores fell into a certain classification represented the height of a class. Another way to evaluate the information is by using, instead of frequency, relative frequency. The frequency relative to the overall number of individuals whose scores that we have. In our previous example, here are our class limits, 50 to 69, 70 to 89, and so on. Now here is a frequency number associated with each of those. And we calculated these frequency numbers before. Now the relative frequency is the quotient of this number with the total number of scores that are in the entire group. Now if we add the frequency numbers, we get 33. So to find the relative frequency for each of these, we would just take each of these and divide by 33. So the relative frequency for this one would be 2 over 33, which is approximately 0.06 or 600ths. And 3 over 33 for this next one would be 900ths, and 2 over 33, 600ths, 9 over 33, 2700ths, and so on. And instead of making our histogram according to frequency, we could make the histogram according to relative frequency. Now, here's what that means in terms of what we had before. Now, let's just slide over here, and here's the graph that we had before. And along this axis, instead of having a number of students, which is a frequency, we will write this as I'm going to erase this, but we're going to write this axis as a relative frequency. And notice that this axis stays exactly the same. That is, the boundaries and the class widths and so forth stay exactly the same. And you know what? If I'm creative about writing in these relative frequency numbers, if I put in 1/10 here, 2/10 here, and 3/10 right about in this neighborhood, then it'll turn out that the graph is exactly the graph that we had before. So there's really no difference in the interpretation of information by using a sort of a frequency histogram or a relative frequency histogram. Now, histogram graphs can have particular appearances that cause them to be able to be placed in certain classifications just by their appearance. There are 4 classifications. Symmetrical means that the histogram sort of rises to the middle and falls to the end. It kind of goes up and down in a relatively symmetrical way. And you know, symmetry has to do with this aspect of a figure, like a graph, where we could actually fold it right down the middle and it would sort of fold onto itself. That's one way to think about symmetry. Or we can think if from a midline it looks pretty much the same left and right. So symmetrical. Now our graph didn't look symmetrical. It didn't kind of rise to the top and go down. It kind of went down gently on one side and it was kind of convoluted on the other side. Uniform or rectangular refers to a histogram in which the frequencies are all exactly the same. It just kind of looks like a box. That's why it's sometimes called rectangular, because all of the classes look like exactly the same box, all next to one another. So it really looks boxy. A skewed left or skewed right histogram is one that kind of is tall on one side and short on the other side. Let me show you what I mean. Now ours is not skewed, but if we started our histogram right about here, then it would be tall on this end and short on the other end. And this would be a classic skew to the right. And if you think about the narrowing to a tail, it's the end where the tail narrows that gives rise to the right or left-handedness of this skew business. So this would be skewed to the right. Now this one, the overall histogram though, is not skewed to the right. And it's not symmetrical. If it were symmetrical, it would go to the top like this, and it has a nice symmetry to the right side, doesn't it? But it doesn't have that kind of aspect to the left. And so it's not uniform, it's not symmetrical, it's not skewed left or right. Let's look at the last one. The last one is bimodal. And bimodal refers to a histogram graph that kind of goes up. It has a high class somewhere maybe to the left, and then it goes back down, and then it goes back up again to approximately the same level as that first high level. Now ours doesn't fit that description either. It doesn't fall into any of those particular categories. If this class happened to be up in this neighborhood, then I would say that we would be falling into a bimodal situation, but it doesn't fit that kind of pattern, so we don't fit any of those. But those are distribution shapes that we can identify from time to time. Let's look at producing the histogram on the TI-83. Now from time to time we'll be looking at graphing calculator processes, and we're going to use the TI-83 for that purpose. You may have a different graphing calculator, and so the process might be slightly different, but generally the concepts will be the same. That is, the general idea of how to perform a certain function will be the same on other graphing calculators. And here, if your calculator is capable of a histogram graph, then certainly the idea is generally the same as it will be on the TI-83. Well, to begin the process on the TI-83, we would press the button marked Stat, and we're doing that in order to enter information. And we want the top item, item number 1, edit. So we will either press the Enter button or number 1, and we get into a menu that looks like this. Now I have already entered the items in L1, which means list number 1. So I've entered the 33 test scores into this list. Now, you may not have gotten a good look at those test scores earlier, and if you're trying to do this with me on your calculator, here is that list of test scores, and you can use this list to enter the items as you wish. You may notice that in the list the items are in order. That is, they are ordered smallest to largest. And that will not always be true, and it isn't necessary for it to be true to enter the information. They can be entered randomly as long as we get them all entered into our list. Well, once the items are entered into the list, and entering is no big surprise, we just press in the number and press enter or the down arrow button, and away we go. We just go to the next item and so on. Just enter the information in order. All right, once that's done, we'll get out of here. I'm pressing second and then the mode button for quit. Second quit puts us on a main screen. We want to go into the menu marked Stat Plot, right here. It's the second function on y equals. So I'll press second, y equals, and we're going to turn on a stat plot. So I'm pressing enter here because it's plot number 1 that I want to turn on. Now you notice that there's an on and an off, and I'm cursoring to the right to highlight the off, cursor to the left to highlight on. I'll press enter here. Now I've turned this plot on. I want to cursor down and select a type of plot. The type of plot that I want is this one. I'm cursoring over to the one that pictures a histogram plot. So I'm pressing enter. Now notice that here is the X list. The list that we have is in L1. That's the default. The frequency of each of these items is 1, and that also is the default. And that's what we want for our particular plot. Now we're just about ready to go, but we have to tell the calculator a little bit about how we want to structure the class widths and so on. If you simply plot from here, you can do that by pressing zoom and then selecting stat plot and which is this, zoom stat. And the calculator will make some reasonable guesses about our histogram plot. But we've already made some calculations, and we'd like to put those calculations into the calculator. And to do that, press Window, and notice the default settings are on board here. We'll enter for the X minimum, we're going to enter the lower boundary of the first class, and that was 49.5. All right, so here's the lower boundary. And the upper boundary of the top class turned out to be 209.5. And the X scale is the class width, and remember the class width was 20. And now we're pretty much ready to go. The Y minimum as -10, I'll enter this as just -1. We just want to contain our frequencies here, and our frequencies, I think the top frequency was 9, so a Y max of 10 will accommodate that. And a Y minimum of -1 will just give us a little room at the bottom of the screen. And then pressing graph, here we go. So it's real easy to produce a histogram plot. And you know what's really interesting too is the way the calculator displays information when we press trace. Pressing trace, now notice we're blinking, the icon is blinking above the first class. And that class has a class boundary. The lower boundary is 49.5, the upper boundary is 69.5. The frequency within that class is 2. And when we cursor to the right, we have similar information for other classes. Here we have, in this class, we're told that the lower boundary is 109.5, the upper boundary 129.5, and the frequency is 9. Pretty neat, and also pretty easy, isn't it? Before going on, let's review just a little bit. We talked about a histogram. Here is the graph that we looked at on the board a little earlier, having to do with 9th grade reading scores. Notice the left side axis, number of students, and that's just frequency on the left side axis, and on the bottom axis was the reading test scores. And we talked all about how to structure this histogram. This really could be called a frequency histogram if we wanted to name it that way, and we might want to do that to differentiate it from a relative frequency histogram. Now remember, the relative frequency histogram is one where the vertical axis, instead of being frequencies, were relative frequencies. And these relative frequencies were in the decimal form of percents, actually. And the graph looked exactly the same as the frequency histogram. All right, now we want to talk about a frequency polygon. The frequency polygon comes from the frequency histogram. And so let's go back to our previous labeling of number of students. And we know that number of students is just frequency. So a frequency polygon just comes from this kind of histogram, and it's rather easy to structure. All we need to do is identify midpoints of all of the classes that we have listed at the bottom of the graph, and I have identified relative midpoints for all of these. And then from those midpoints, just identify a point at the top of the bar from those midpoints, kind of like this. And then we always want on a frequency polygon to begin at 0 and end at 0. So we'll identify a point at the beginning of the graph, at the beginning of or at the left part of that horizontal axis, one class width away from that 60 mark. So we'll just go one class width over this way. And at the right, we're going to do the same thing. Look at 200, and we'll identify a point one class width over here. And now it's a matter of connecting the dots. Usually the bars are not used when we connect the dots on a frequency polygon. But this is what the frequency polygon looks like. Incidentally, the notion of polygon would be obvious here. Polygon is a many-sided figure composed of straight segments, but the closure of this would come from connecting the first dot with the last dot down at the bottom. I haven't done that here, but you can imagine what that would look like. At any rate, the frequency polygon emphasizes the continuous rise or fall of frequencies in a particular kind of study. So that is its usefulness. Let's talk about cumulative frequency now. We are accumulating frequency. That's what cumulative frequency is all about. And it's used to determine how many scores are above or below some kind of set level. And then we're going to construct the graph of those cumulative frequencies, and that graph is called an ogive, a graph showing cumulative frequencies. Let's talk about how to calculate cumulative frequency first. Here is this is a chart. This is information that we had on the board earlier having to do with those 9th grade test scores. We identified classes or classifications for the test scores. We had frequencies associated with test scores that fell within particular classes. We identified relative frequencies. Now, we really don't need relative frequencies for our discussion of cumulative frequency, but just for completeness and to differentiate among them, I wanted to include this column in the graph. The relative frequency of 0.06, remember, was found by taking the frequency of 2 and divided by the total of the frequencies, which was 33. So 2 over 33 was 0.06. And for the 0.09, it was 3 divided by 33, and so on. So that's what relative frequencies are all about. Now we can continue with this chart arrangement and list cumulative frequency in a column like this. And cumulative frequency means we are accumulating frequencies as we go down the chart. The first item in the cumulative frequency column would be a 2. The next item is a 5 because it's the sum of 2 and 3. And the next item in in line would be 2 plus 3 plus 2, which is 7. And we would continue in a like manner. Now, we can, for the next one, it would be the 7 that we just arrived at plus the very next one, which is 9. 7 and 9 would be 16 to give the next item. And we can continue like that all the way to the bottom of the chart. So here we have a list of the cumulative frequencies. And it is at this point that we can begin to talk about constructing the graph, or a cumulative frequency graph, or an ogive. Now, to do that, though, we need to identify class boundaries, because the class boundaries are going to be useful in constructing the graph. Now, you may remember that the class boundaries, the lower and upper boundaries, are just a difference of 0.5 from the various classes. And just at 0.5 smaller than the lower number of our class boundaries would give the lower class boundaries. The lower number in those classes, for example, the top one is 50. Take 0.5 away from that, we get 49.5. And then for the others, all the way down the line, it's just 0.5 smaller than all of those. See, 0.5 smaller than 70 is 69.5. Same with all of them. The upper class boundaries is just 0.5 larger than the numbers listed as the top number for the classes. So it would be these. And it's not like there's a great deal of calculation that's done here. We notice very quickly that the upper class boundary for one item is the same as the lower class boundary for the next item. So it's very easy for us to generate a chart like this. Well, let's talk about making the graph now, the ogive. And we would begin by structuring the first quadrant of a coordinate plane, and then we would go about the labeling process. On the left side axis, we're going to be talking about cumulative frequency. And we might think, well, gee, how do we make this cumulative frequency? Where do we start? Where do we end? Well, we're going to start with 0, but how far up do we go? Well, the cumulative frequency total is 33, and we can see it down here. So we want to go on the left side axis with some number just above 33, and I've chosen to go with 35. On the bottom axis, we're talking about reading test scores, and we're going to begin with the lower boundary of the first class. So we're going to start with 49.5. And then from there, we're going to use the upper boundaries. So we're just going to make our lower axis like this. Now, using this lower axis labeling, we'll begin by putting a dot at the 49.5. You see, at the very beginning from left to right of the arrangement. And then for all of the other marks, we're using those cumulative frequency numbers. For 69.5, we're going to identify the point 2, you see. And then for 89.5, we're going to go to the cumulative frequency of 5. And then for all of the others, we're going to go up to their cumulative frequencies from the chart as well. And then it's just a matter of connecting the dots. And now we can make an interpretation if we want to. It's pretty easy to interpret how many test scores are below any particular level. For example, if we want the test scores below the level of 129.5, we just look up at the graph and then turn our attention to the left side axis, and we see, oh, there are 16 scores that are below 129.5. Before we leave this topic, let's talk about some differences that we've noticed between the frequency polygon and the ogive. Now, for the frequency polygon, the points are graphed above class midpoints. That's an important characteristic in structuring the frequency polygon. Whereas with the ogive, the points are graphed above the upper class boundaries primarily, except for that first one was the lower boundary of the first class, if you recall. So primarily it's upper class boundaries, though, that are important on that horizontal axis for the ogive. Also, the vertical coordinates are class frequencies for the frequency polygon, and the vertical coordinates are cumulative frequencies when we structure the ogive.